Autodesk Maya has long been regarded as a leader among 3D graphics packages. Maya's nearly limitless tools enable artists and designers to visualize almost anything we can imagine. In particular, Maya really shines in the area of materials and shaders. My name is Aaron F. Ross, and I'd like to welcome you to this course on Maya Advanced Materials. I'll start the course by sharing some essential tips and tricks for the Hypershade to accelerate your workflow. Then you'll learn about designing physically based materials in Maya using the new standard surface. We'll take a look at ray tracing techniques for translucent and transparent materials, and also how to apply surface relief using bump, normal, and displacement mapping. Maya is the gold standard for power and flexibility in material look development, so let's apply that creative power in this course on Maya Advanced Materials. If you have access to the exercise files I've created for this course, you can go ahead and download those and extract them to a convenient location. I've placed them here on my Windows desktop. Let's take a look at what's in the exercise files, and in a moment we'll set Maya to point to this project. This is a standard Maya project folder. Most of the subfolders are actually empty. The important folders here are scenes and source images. In the source images folder, we will find all of the textures and environment maps for the various scenes. You'll also see that there are .tx files in here. These are automatically generated by Arnold, and I've included them here in order to speed up your load and render times. In the scenes folder, we have a bunch of Maya ASCII scene files. Generally, there is one scene file per movie that represents the state of that movie at the beginning of the exercise. In a few cases, there's also a finished example that illustrates the end state of that exercise. You'll notice that these scene files are very, very small, and that's because they're referencing another scene in order to save disk space. In the referenced scenes folder, I've got a larger scene file that's about 35 megabytes in size, and it's being loaded or referenced into the scenes for each movie. Scrolling down to the bottom of the list, there's also a text file down here, modelcredits.txt. Open that up. These are the credits for the stock model that I've used for the exercises. It's called Figure of a Dancer. The artist was Agathon Leonard, and the model was provided by the Smithsonian Institution. It's downloadable from sketchfab.com. All right, let's go into Maya. I've got that minimized. The first thing I want to do is strip down the interface a bit because we're not going to be using most of these UI elements. I'll go into Windows, Settings Preferences, Preferences, go into the UI elements. I'm going to turn off a lot of this stuff. Turn off the shelf, the time slider, the range slider, the command line, and also in the main interface category, I'm going to turn off the title bar in the main window just to save a little bit more space. Okay, I'll click Save to save those preferences. I also want to hide the toolbar in the viewport, and that can be done with the keyboard shortcut Control-Shift-M. Now I've got a stripped down interface that's appropriate for teaching a very focused area of Maya, which is advanced materials. Now we're ready to set up our project. If you're not following along with the exercises, for example, if you don't have Maya installed or if you're on a mobile device, you can still learn by observation and note-taking. If you don't have the exercise files, you can still follow along with the demonstrations using your own assets. In that case, you'll want to create a project for the course. We can do that from the menus. Go to File, Project Window. In the Current Project field, click the button labeled New and give it a name like Advanced Materials and press Enter. It will be stored in the default location, which is your current user's Documents Maya projects. But of course, you can navigate to some other location if you want. Just click Accept, and you've created a new project folder. If you're going to be using the exercise files I provided, you'll want to set Maya to that project folder. Go into the File menu once again, and choose Set Project, and navigate to the desktop in my case, and just choose the root level, the folder labeled Exercise Files, and click Set. And then when we go to the File menu and choose Open Scene, we're taken to our current project's Scenes folder. That's how to set up the exercise files for the course. I'd like to begin by talking about the creation options for new nodes in the Hypershade. Maya gives us many options for creating nodes. We can do it in many ways. However, there is a bit of an issue that can come up when creating new nodes, and that is that certain types of nodes, such as cameras and lights, are going to be added to the shading network graph by default, and we usually don't want that. So let's see how we can create nodes. I'll open up the Hypershade by clicking on its button on the status line. The most obvious way to create nodes is from the Create panel. For example, we can go to Favorites, Maya, and click Standard Surface. And that's going to create the node in the browser here, and it'll also graph that node or nodes. And we can zoom in on that a little bit. Right-click in the graph and choose Select All in Graph from the marking menu, and then frame those nodes with the F hotkey. That's the default behavior when creating a new node, either from the Create panel here, or from the Create menu here, or by selecting an object and then right-clicking and choosing Assign New Material. If you use any of those methods, then the new nodes will be added to the graph by default. And that's usually what we want when creating new shading nodes, but other types of nodes such as lights and cameras will be added to the graph by default as well. So I don't really want that. Let's erase these nodes. I'll select those and press the Delete key, and I'll create a light. Go to the Create menu and choose Lights, Point Light, and it's added to the graph. It's also in the Lights tab of the browser. I've got a new point light that I didn't have before. I'll select that and delete. If we don't want to add any lights or cameras to our graph, then we can disable an option, and it's found in the right-click marking menu once again. Right-click in the graph and disable Add to Graph on Create. And you probably want to check and make sure that's actually off. Right-click again, and we can see that it's been disabled. Now if we create a light or a camera, it will be created and added to the Lights and Cameras tabs in the browser, but those nodes will not be added to the shading network graph here. I can go to Create, Lights, Point Light, and it does show up here in the browser, but it is not added to the graph. Okay, I'll undo that with the Z key. That's helpful because it prevents a lot of clutter in the graph. However, disabling Add to Graph on Create does create a little bit more work for us if we're used to using the Create panel. So I'll go back to my Materials tab, and if I click on Blend, for example, a new blend node is created, but it's not added to the graph. If I wanted it to be in the graph, I could select that node, and I could click on Show Input and Output Connections. All right, or I can clear the graph out. Or I could merely just middle mouse drag that node into the graph. Okay, disabling Add to Graph on Create does solve the problem of those light and camera nodes being added to the graph, but it does make things a little bit harder for us if we're used to the standard method of creating new nodes. However, there is a creation method which will automatically add the new nodes to the graph regardless of the state of the Add to Graph on Create option. And so to illustrate, I'll clear the graph once again, and if the graph is empty, we'll see a message saying press Tab to create a node. We can use the Tab key to create any node if we know the name of that node, whether the graph is empty or full. So let's press the Tab key. We get a search box, and we'll type in STA, and the first hit here is Standard Surface. So click on that, and now we created the standard surface as well as its shading group and added it to the graph, despite the fact that Add to Graph on Create is currently disabled. That option is stored in every individual scene for the Hypershade. So if we turn that off and then open a new scene, it will probably be turned back on again. The node editor does have a user preference for this, but the Hypershade does not. That's how to control whether or not new nodes are added to the graph. Now I'd like to streamline the Hypershade in order to maximize efficiency, both in the workflow for the user and for the performance of the workstation. Currently, I've got a pretty low resolution desktop for the screen capture, and under these conditions, I've got very little screen area for the actual graph. I'm going to need to close up some of these other panels in order to make some space for the graph. And additionally, that's actually going to help my workflow and performance. Let's start with this material viewer. If you select any node, then you'll see a preview of that material. But by default, that's going to be rendered in the Hardware 2.0 or Viewport 2.0 hardware renderer. We could switch the renderer over to our production renderer, which is Arnold in this case, but that could actually cause more problems than it solves, because the material viewer will not be able to update if you're running Arnold in some other window, such as a viewport or the Arnold render view. Additionally, we have very limited control over the test object and the lighting within the material viewer, so I recommend that you do your material testing in an actual scene with real lighting and an actual real model. So this material viewer is not really of much use to us. I'm going to close that by clicking on the little X in the upper right corner. Then we come to the property editor. And this is just a version of the Maya attribute editor. And in fact, it's completely redundant. And since the Maya attribute editor is such a key component of Maya, I find that I need to have it open almost all of the time. And if the property editor were open at the same time, I'd be looking at all the same attributes twice. Additionally, certain commands will cause the attribute editor to open automatically, and that would again be redundant to the property editor. For example, if we assign a material through the viewports, that'll cause the attribute editor to open. If I select an object and then right-click and choose Assign New Material, I get the Assign New Material window. Let's click on Standard Surface, which creates that node and assigns it to the selected object, and it causes the attribute editor to open automatically. Move the Hypershade over and select the Standard Surface. We see that we've got the same thing displayed twice. Okay, well, I'm not going to use the property editor. I'm going to close that by clicking on the little X. Additionally, I'd like to float the attribute editor. So I'll grab its tab and just move it out, and then lock the Maya user interface layout from the padlock in the upper right corner, and that won't cause the attribute editor to attempt to dock to anything. By the way, that little lock icon does not work for the Hypershade. So we can drag things around in the Hypershade and put them somewhere else, even if this lock icon is enabled. So that's a little bit of a gotcha. Then we come to the Create panel. As we just saw, and as we saw in the previous movie, there are many ways to create shader nodes, and there's really no need to have this Create panel open all the time. So to reclaim some more space, I'm going to close that as well. Click on its little X button. Then we come to the bins, which are ways to filter the display. We'll talk about that later. For now, I'm going to close the bins panel as well. Now I'm just left with the graph and the browser. And this is a pretty stripped down version of the Hypershade. For the purposes of my screen capture here, I'm going to want to make this browser as small as possible. And if we click and drag on this divider line here, we see that there's a limit to how small we can make that browser pane. But I can reclaim a little bit of space by floating that browser pane in a separate window. So I'll grab that textured bar and then drag, and now I've got the browser in a separate window, and I can resize it to whatever size I need and position it, maybe change the size of my graph window. So now I've just made it so that I've got enough space to actually work. Then we come to the swatches. So in each of these tabs, we'll see swatches for the various nodes, and those are going to have to render. We're going to have to wait for those to actually calculate. And if we make changes to the shader network, these swatches are going to have to update as well. And that could really slow down performance. One option would be to turn off swatch generation just globally. We can turn this button off, and now swatches will not be rendered anywhere in the Hypershade. But that includes our graph. And I probably do want to see some swatches in the graph. Just so we can see what we're looking at here, I'll drag a selection rectangle around those two nodes and press the F key. So we do have a swatch here for this standard surface, and we can make that larger if we wanted. We've got a button here to increase or decrease the size of the selected node's icon swatch. So we can use this swatch to sort of preview our material here in the graph, but it won't update if this swatch generation switch is off globally. So I do want that to be on, but I don't want the extra performance overhead of all of these swatches re-rendering every time I make a change. So the solution to that is just to display these as a list rather than as icons. So we got another button up here, View as List. Click on that, and now we just see the names of those nodes. But they're kind of small. The names are actually getting cut off or truncated. We can increase the size of those by clicking on this button here, View as Extra Large. Now we can see all those names. Those settings are unique to each one of the tabs, so I want to go into Textures and do the same thing, Display as List and Display as Extra Large. We could go into the rest of these, maybe Utilities, and do the same. Those are really the only three I'm going to be using, Materials, Textures, and Utilities, so I can just leave the rest of them alone. So now I've optimized Hypershade for usability as well as performance. As we'll see, the Autodesk standard surface material is physically based and designed to be renderer agnostic, meaning that it will work with almost any renderer. However, regardless of that, you're going to need to set up your specific renderer before you begin any material look development. And that's because you need to optimize performance as well as renderer options such as the ray depth. Otherwise, your test renders of materials may not give you an accurate representation of what you'll get in a production rendering. In this course, I'm using the Arnold renderer, which is the default in Maya. So let's check in on the Arnold renderer settings. From the status line, click on Render Settings. And we want to go into the System tab and choose whether we want to render on the CPU or the GPU, or the graphics processing unit. Generally, you want to render on the CPU, but if you've got a good graphics card, you might try using the GPU rendering. We don't have much time to talk about the Arnold settings in this course. You might want to take a look at my other course, Maya Rendering with Arnold 6. For the purposes of this course, I'm going to leave the render device at CPU. Then we come down to the render settings here, and we can choose how many threads or processor core equivalents we want Arnold to use. I'm going to leave that at auto detect, and that means when I do a production rendering, Maya will use all of the available CPU time. For doing test renderings, we can choose to throttle the processor usage in the viewport or the Arnold render view, and this setting will not actually affect the viewport or the Arnold render view. So I'll leave all of this as it is. But going over to the Arnold renderer tab, we will want to go into the ray depth section and make sure that we have enough rays. I've got this scene set up for 4 diffuse rays, 4 specular rays, and 8 transmission rays. And that's important because later I'm going to have a glass case around this sculpture, and I need to have enough specular rays to generate the reflections inside that glass case, and I need enough transmission rays in order to render all of the transparency. If you're seeing black parts of your rendering, you'll probably need to go into the ray depth and increase the specular or transmission rays. While I'm here, I can also enable progressive render, which is useful for interactive production rendering while we're testing our materials. That's just going to give us a little bit better feedback faster. So instead of seeing buckets drawn on the screen, the pixels will update randomly, and that'll give us feedback a little bit more quickly. With these options set up for a look development workflow, I can go ahead and save a preset. So I'll go into the Render Settings menu and choose Presets, Export Render Settings. And I'm taken to my current user's documents Maya presets. I'll save a preset for these render settings. Let's call it Look Dev for look development. LOOK_DEV. And click Save. And now if we go back into Presets and go to Import Render Settings, User, we can see that our preset is there. So if we make any changes, for example, set this up for a production render with maybe greater samples or no progressive render for a production rendering, then we can save a preset for that as well and then switch back and forth between them using that menu. All right, we've got the Arnold renderer set up for look development or material testing. If you're using another renderer, you'll need to follow an analogous workflow, checking in on your processor usage, as well as the sample quality and the ray depth of the renderer. To get an accurate read on your materials during look development, you'll need to have a scene set up for material testing, and that could be the same scene that you're going to use in production, or it could be a scene set up specifically for material testing. In this case, I'm using the scene that I'm going to render in production. It's this simple museum layout, and I've got a bunch of lights here, but currently the only one that is enabled is the spotlight that's shining on this figure of a dancer. And that's fine for a diffuse material, such as the porcelain that we're going to create for this figure. If you're testing very shiny reflective materials, then you might want to use a high dynamic range sky dome in order to generate reflections on all the surfaces. We'll take a look at that later in the course when we get to material development. For now, I just want to talk about interactive production rendering in Maya using Arnold. We can do it in two ways, either within the viewport or from the Arnold render view. And again, we don't have a lot of time to cover all the features. If you want to learn more about this, check out my other course, Maya Rendering with Arnold 6. To preview materials in the viewport, all you need to do is choose Arnold as the current renderer in that viewport. In the menus, choose Renderer, Arnold, and you get a little pop-up window, which is the Arnold options. And you might want to throttle the rendering so it doesn't take up your entire computer CPU time. And you can do that by going into the Render menu here. Save UI threads. And it's set to a value of 1, meaning that Arnold is going to use all of your computer's available CPU core equivalents minus 1. Well, I recommend that you set this to a value of 2 to allow a little bit more processing overhead. For the purposes of this course, just to make sure that I don't have any hiccups on my screen, I'm going to set Save UI Threads to 3, and that means that Arnold will leave 3 core equivalents open for other things such as manipulating objects and changing shader parameters. So I'll set Save UI Threads to 3 for the viewport, and we can initiate the interactive production rendering by clicking on the red triangle, which is supposed to be a play button. And now we see Arnold render in the viewport. And that is fully interactive. We could, for example, select objects and maybe grab the Move tool and move those around and click to deselect, and we see that Arnold updates immediately. Okay, I'll undo that movement with the Z key. Click Z a couple times to send that back where it was. That's one option. We can render directly in the viewport. I'll switch the renderer back over to viewport 2.0. For comparing different versions of a material, you'll probably want to use the Arnold render view because it gives you the ability to create snapshots. So we can go to the menus to Arnold, Render, and it's going to render the active viewport by default. It's also going to render using the current render resolution. And we can see that down here in the lower left, 1360 by 768, 1:1. And that is my production rendering resolution. We can knock this down to a fraction of that, and that will cause it to render more quickly and also take up less space on the screen. So I can press Stop up here and go into the Arnold Render View menus to View, Test Resolution, and I'll knock that down to 50%. And now when I press Play or Start, it re-renders. At first it looks kind of fuzzy, but that's just because we're zoomed in to 200% size. So we'll just click on the button here, 1:1 or real size, and now we're seeing the rendering at half of the production resolution. Additionally, we'll want to throttle the processor using Arnold Render View. That's done from the menus once again. Go to Render, Save UI Threads, and just as in the viewports, we can set this to limit the processor usage. Once again, I'm going to set Save UI Threads to 3. That's how to set up interactive production rendering in the viewport or the Arnold Render View. Maya is very powerful and flexible. However, sometimes the Maya interface can be problematic. And I've been using Maya for 20 years, and I've always said if you can just see it and select it, you're halfway there. And that applies to the Hypershade probably more than anywhere else in Maya. Unfortunately, the Hypershade window, as of Maya 2020, still has a number of issues and bugs, and I'm going to try to help you sort through all that. So first of all, let's talk about graphing shader networks. I've got my browser docked back onto the Hypershade window once again. If we select a material node such as Dancer STSF, We can graph all of its connected nodes by clicking on the button Input and Output Connections on the Graph toolbar. Click that button, and we should see all of the nodes connected to that material, and it should be auto-arranged so that everything is nice and clean. By default, additive graphing is enabled, and that means if we graph some other shading network, it will be dropped into the current graph. If we right-click in the graph from the marking menu, we can see additive graphing mode is on. So now let's graph another material. Select Parquet STSF. Once again, click Input and Output Connections. All those nodes got dropped onto the existing ones. And by the way, very importantly, commands to change the display of the graph itself are not undoable. The undo command will only respect the selection of nodes and changes to their attribute values. So I can't just hit undo and clear out the last display command that I've done here. We could try to rearrange the graph. If we click on that button, that might work in your case, but in my case, because of the small size of my screen, I was not able to rearrange the graph. However, I can select and move a bunch of connected nodes all at once. If we select a single node, we have some commands to select the upstream and downstream nodes. And that can be done from the marking menu once again. You can right-click and choose Select Items in Stream, select Upstream, select Downstream, or select Upstream and Downstream. And once you've done that, then you can move all those as a unit. You probably don't want to use that marking menu. There's a hotkey for that. Select a node, and to select all of its upstream and downstream nodes, use the / key on your keyboard. So that selects all of them. If you just want to select the upstream nodes, that's the comma key on the keyboard. If you want to select the downstream nodes, it's the period key. Okay, once I've arranged this, I can try rearranging once again. And we can see that this time, because I had manually moved those nodes over, the graph actually rearranged properly this time. Let's talk about framing selections. If you select some node and press the F key on the keyboard, then Hypershade will frame the selected node. However, this is a global hotkey, and its behavior is different in the Hypershade than it is in other parts of Maya. So for example, if we go over to our viewport and select nothing and press the F key, it will actually frame everything in the view. However, if you select nothing in the Hypershade and press the F key, nothing happens. Additionally, in the Hypershade, there is no hotkey to frame all. You have to select everything and then press the F key. There are also no hotkeys to rearrange the graph. There's no hotkey to change the size of swatches. And these are all things that you'll need to do all the time. In the next movie, I'll show you how to bind some hotkeys in order to get access to those commonly needed commands through the keyboard. That's a bit about how to graph networks using Hypershade. In the previous movie, we saw some of the most common commands for graphing and displaying shader networks. Now let's talk about binding hotkeys to some of those commands because we're going to need to use those quite a lot. So for example, one of the most common commands is to graph the input and output connections. I've got my browser attached here to the Hypershade window. In the Materials tab, I'll select the Dancer STSF material and click Input and Output Connections, and we see the entire shader tree displayed. There's no keyboard shortcut for Rearrange Graph, which is something we need to do constantly. There's also no keyboard shortcut to toggle the size of the icons, and there's also no keyboard shortcut to frame all in the graph. We can frame selections, and that's a Maya global hotkey. So if I select a couple of nodes and press the F key, we'll zoom in to frame those too. But if I select nothing and press the F hotkey, nothing happens. So I'm going to bind a hotkey to the Hypershade command to frame all. And I'll also bind hotkeys to those other commands I mentioned. Go into the main Maya menu and choose Windows, Settings Preferences, Hotkey Editor. Before making any changes, we want to create a custom hotkey set. Because if we start defining hotkeys, Maya will automatically duplicate this default hotkey set and give it a default name. So let's start out by creating a custom hotkey set. Click on the gear icon and choose Duplicate. And in the pop-up window, give it a name. We'll call it custom_hotkeys. And click OK. We can search for application commands down here. We've got a search field. So the first one I want to bind is Hypershade Frame All. So let's type something in here. HYPERSHADE space F. And now we see Hypershade Frame All and Hypershade Frame Selected. Over here on the right is the hotkey column, and we see nothing there, indicating that no hotkey has been bound to either one of those commands. We saw that we are able to frame selected nodes in the Hypershade, and that is again because the F hotkey is global to all of Maya. Let's now define a local Hypershade hotkey for Frame All. Select that command, and over on the right we can type in a new hotkey combination. You want to do this very carefully, because if you slip up, you'll end up defining a hotkey you don't want. You may actually erase some other hotkey, and it's actually kind of fraught with peril. So do this very carefully. Hold down the Shift key and press F. That's going to be our hotkey to Frame All, Shift F. Go down to the bottom and click Save. Don't click on anything else, just immediately click on Save. Now let's define another hotkey. We'll clear out this search term by clicking on the X, and now we'll search for Rearrange, R-E-A-R, and we see Hypershade Graph Rearrange. Click in the hotkey field, and we'll define that as the key L. And that's similar to a command in the node editor to lay out the graph. So use the L keyboard shortcut and click Save once again, and then clear out the search term. We'll search for our next command, which is to toggle the size of swatches. So let's search for swatch, S-W-A-T-C-H. And we want to scroll down a little bit. We're looking for Hypershade toggle node swatch size. And we can give that the hotkey of V for Victor and click Save. I have one more I want to bind, which is input and output connections. So let's clear out that search term once again. And unfortunately, the command in question is not actually called input and output connections. Even though that's what it's called in the Hypershade itself, inside of Maya, it has another name. So you're going to find this quite a lot, that a particular command is always going to have at least two names. It's going to have its friendly application command name. It's going to have its runtime command name, which is for scripting. Then it will also usually have some menu name and or a tooltip name. And those are all different. And they can be very different. So sometimes it's really difficult to find the command you're looking for. And you need to actually go through the categories and sort of search through manually. But I've done that already. So I know that the command I want is actually not called input and output connections. It's called Hypershade Graph Up Downstream. So let's start typing that in. Hypershade Graph Up, and we see Hypershade Graph Upstream, Hypershade Graph Up Downstream. And this one is already associated with a hotkey, which is the question mark. And that's a little bit more difficult than it needs to be because we need to use the Shift key to access the question mark character. So let's just reassign this. I'll use the C keyboard shortcut, C for connection. So click in there, type in a C, and then click Save and Close. And now we can test our work. Click in the graph to select nothing, and we'll try the Frame All command, which is Shift F. All right, that worked. Let's clear out the graph and try one of these other commands. I can select the Dancer STSF material and graph that network with the C key. All right, that one worked. We can try the Rearrange command too. We can move things around and then press L. Okay, Rearrange is working. And then finally, the swatch size, or the size of the icons. And that's this button up here. Let's try the keyboard shortcut we just made, which is V for Victor. Okay, we can click V again and turn that back the way it was. That's how to define keyboard shortcuts for the Hypershade. Maya nodes can have many attributes, And we want to be able to display just the necessary information in the graph so we can avoid clutter. Right now I've got the Hypershade maximized so we can really see what we're working with. Let's talk about how to manage the display of these attributes here. We've got some buttons up here on the graph toolbar. Hide attributes on selected nodes, show connected attributes on selected nodes, show primary attributes on selected nodes, and show custom attributes. Well, what do these do? Well, if we click on one of these buttons with nothing selected, then it will do something to the attribute display for all of the nodes in the graph. So that first one there is to hide all the attributes. Then the next one is show connected attributes, and that will show any attributes that are actually connected to something and hide everything else. So we can see here for this dancer standard surface, the only things connected are the base color and the normal camera or the bump map channel. All right, I'll deselect that. And moving on, we have the third button up here, which is show primary attributes. Click on that. And that's actually going to display pretty much all of the attributes. And it can be quite a lot of them. And we can navigate around here with Alt and middle mouse button. So for this standard surface, we see we've got many, many attributes, and that's quite overwhelming. So we don't really want that. Then we have the last icon here, which is custom attributes. And that one is probably the most useful, and it is the default. So if no nodes are selected and we click on that, then we're going to see the custom attribute display, which is the attributes that the developers have determined we will need to use most commonly. And I can rearrange the graph. So now I'm back to sort of the default layout here, which is we're seeing the custom attribute list. There are keyboard shortcuts for those 4 commands. You probably want to get used to those. If I have nothing selected and I press the 1 key, we'll hide all the attributes. The 2 key shows only the connected attributes. 3 shows all of the attributes. And 4 shows the custom attributes, or the ones that are most commonly used. I also want to share with you another important keyboard shortcut, which strangely is not associated with any icon or any menu command, and that is to display the node name or the node type or nothing up here in the node header. And the keyboard shortcut for that is 5. So when you click on the 5 button on your keyboard, you're toggling between 3 states. So the default state is to display the node name. Press the 5 key, then we see the node type. Press the 5 key again, and then we see nothing. All right, I'll press it once again and go back to the default behavior. There is a strange exception to this behavior, which is if the node is a bitmap file node, then we will never get to see the name of the node. Instead, we will see the name of the file that is referenced by that node. So to illustrate, if I select this node, which is dancer4096 occlusion.png, and open up the attribute editor with Control A, we can see that it is a file node and it has a name. I've named it dancer occlusion bitmap, but we will never get to see this name displayed in the graph. And this is problematic if you really need to see the node names for file bitmap nodes. We're not currently permitted to see those in the graph, but only in the attribute editor or in the outliner or anywhere else where the actual node name is displayed. That's how to control the display of attributes as well as node names and node types in the Hypershade graph. If you've got a complex graph with many nodes and attributes, then you may wish to filter the display based upon a search term. So for nodes, we can search up here from the toolbar of the graph. So for example, if we want to find just the normal map, then we could type something in up here. But if we just type in normal and press enter, we don't see anything at all. And that's because we need to supply some wildcards. So if we go up here to the search field and put a star or an asterisk in front of normal and another one after normal and press enter, now this actually shows up in the display. So this is a way of filtering based upon a search term, and we need to use wildcards. This is a very important thing. So if I now search for example, dancer, and press enter, again, I see nothing. But if I search for dancer star and press enter, then every node that has the word dancer in its name will show up in the graph. Okay, I'll clear out that search term by clicking on the X, and now we're back to not filtering anything. If you want to filter attributes, that's done on each node. And if you're displaying the connected attributes or displaying all of the attributes, then by default you'll see a search field on the top of each node. For example, if I go up here to show connected attributes, then now I have a field up here at the top of the node. For example, I can go over here to this normal map and type in UV, and now every attribute that has the letters UV next to each other is displayed. And here I did not need to use any wildcards. Okay, I'll backspace, and now I'm displaying all of those attributes once again. And that will work if we're showing the primary attributes or all of the attributes as well. For example, I can go over to this standard surface material and type in a search term BASE for base. We have the base weight and the base color. Erase that and go back to displaying all of the attributes. If we're in custom attribute display mode, then that field disappears up here. But we can actually bring that back by clicking on the magnifier glass here. Toggle the display of the attribute filter field. And now we can go back to searching once again, BASE, and everything that doesn't have that string in it is hidden. All right, I'll erase that and switch that back off again. That's how to filter the display of nodes and attributes. Node presets in the attribute editor can come in quite handy for material shading workflows. We can use node presets to store and recall from a library of materials, transfer attribute values between shading nodes, and create variations on a theme. Node presets operate on specific node types, such as a camera shape or a standard surface material node. We can save or load all attribute values of a single node type. This won't help if you need to store an entire shading network, but for monolithic node types, such as the standard surface, attribute editor presets are very useful. I've got the Hypershade open with the material browser visible. I just want to show you I've got a couple options enabled in the graph. Right-click in the graph, and you can see I've got Add to Graph on Create enabled, and also Additive Graphing Mode enabled. In the material browser, select Frame Gold STSF, and graph its input and output connections. And with it still selected, open up the attribute editor with its keyboard shortcut, which is Control-A. In the attribute editor, we'll see a button labeled Presets. And if any presets exist for the currently selected node type, we will see a little asterisk or star next to the word Presets. Click on that button to access the menu. We can see that for the Autodesk standard surface material, the developers have provided just a few default materials. I don't want to lose what I have here, so I'm not going to click on any of these. I'll just click off that menu. Instead, I actually want to save this standard surface preset, Frame Gold STSF. Go back to the Presets button, click on that, and choose Save Standard Surface Preset. We need to give it a name. The default is just the name of the currently selected node. That works fine in this case. I can just erase everything after Frame Gold because it's obviously a standard surface. Click Save Attribute Preset. And now that's been stored and I can easily recall it. For example, I can just reduce the base weight and base color. And to undo those changes, I can go back up into the Presets button. And at the bottom now I have a preset Frame Gold. I'll choose Frame Gold, Replace. And now I'm back at that gold material. In the viewport, select one of the frames and assign a new standard surface material. Right-click in the viewport, hold down the mouse, and from the marking menu, choose Assign New Material. In the Assign New Material window, click Standard Surface. And now we've got two standard surfaces here. Let's clean up our graph a little bit. Click in the graph to select Nothing, and then let's display none of the attributes. Also toggle the icon size and rearrange the graph. Here's the first one, Frame Gold STSF. Here's the new one we just created. So with Standard Surface 2 selected, we can go back up to Presets. Once again, load that Frame Gold and choose Replace. Now I've got two different materials on two different objects, but they have the same attribute values. This new one, Standard Surface 2, will be copper. Let's change its name. I'll call it Frame Copper STSF. And press Enter. Then just change the base color. We'll click on that color swatch and change the hue to be more red, and maybe increase the value and reduce the saturation a little bit. And once that's done, we can see that we've got a different color here. If we want, we can save that as its own preset. Once again, click on Presets, Save Standard Surface Preset. I'll just call it Frame Copper, and save. The user-created presets that we see when we go into that menu are listed at the bottom here. The developer-created presets are up here, and those are in two different folders. If you want to back up your presets or send them to a different workstation, you'll want to know where they're stored. I'll minimize Maya. Presets are stored in the current user's documents, Maya, version number, presets, attribute presets. And there will be a folder in there for each node type. If I go into Standard Surface here, we'll see I've got framecopper.mel and framegold.mel. The presets that come with Maya are in the Maya application directory. I've got that open here too. On Windows, that's going to be in the system drive under Program, Autodesk, Maya 2020, Presets, Attribute Presets. And I've got some here for Standard Surface. If I go up one level, we'll see that there are a bunch of other node types that have stock attribute editor presets provided with the Maya installation. That's how to use node presets to store attribute values for material shading nodes. The Bins window provides an easy way for you to organize material shading nodes. You can use any system of categorization you wish. I've got the Bins window hidden, so I'll reveal that from the Hypershade menu. Window, Bins. It appears in a floating window. I'll dock it to the lower left, which is its default position. I'm also going to dock the browser on the left here too, just to take up less space on the screen. Click and hold on the textured bar at the top of the browser pane and drag it over to the upper left of the Hypershade window. I'll also resize that so I can get two columns. And I'm displaying large swatches and viewing as a list. Currently, the master bin is selected and active. The master bin is all of the shading nodes in your scene. Let's create a new bin to filter the browser display and display only some of the shading nodes. I'll select Frame Copper, hold down Shift and select Frame Gold, Frame Silver, and Frame Silver AIAO, which is an ambient occlusion node. With all four of those selected, go down to the Bins toolbar and click Create Bin from Selected. We need to give it a name. We'll call it Frames. And click OK. Now we've got a new bin in the list here. If we click on Frames, we'll see only those four materials. Click on Master Bin, and we're back to seeing all of the materials. Let's make another one for the pictures. Select Picture Falls, hold down Shift, and select Picture Lighthouse and Picture Shire. Once again, create a new bin from the selected nodes and give it a name, Pictures. Click OK. Now we've got two bins, Frames and Pictures. To add nodes to a bin, you just middle mouse drag. I can go back to Master Bin, and I want to bring this matte material over as well. Select it and middle mouse drag it over into the Frames bin. Select Frames, and we see it's been added to that bin now. Additionally, any dependent nodes of these materials will be visible within their respective bins. For example, if I go to Pictures, we'll see I have pictures of a waterfall, lighthouse, and a landscape called the Shire. If I go to the Textures tab in the browser, I see the corresponding bitmap nodes. Go to the Utilities tab, and I see the corresponding 2D texture placement nodes. Okay, bins are pretty easy to work with. I can go back to the master bin And back to my Materials tab once again. That's how to use bins to organize material shading nodes. In this chapter, we'll take a first look at the Autodesk Standard Surface material. It's an all-purpose physically based material that is designed to be renderer agnostic, meaning that it should look pretty much the same when rendered in any physically based renderer. Before we start working with the standard surface material, we need to set up the scene for material design and testing, also known as look development. A good practice is to illuminate the scene with a high dynamic range image, and I've done that using an image from a website called hdrihaven.com. I'm using an Arnold Sky Dome light here in the scene. To learn how to set that up, you can see my other course, Maya Rendering with Arnold 6. I just want to show you the setup that I'm using with that Sky Dome so that you can reproduce it. I don't want the Sky Dome to show a background in the test rendering. That's distracting. I only want to see the lighting, not the backdrop. And to do that, I've positioned the Sky Dome light where it will not be visible in the viewport. If I zoom in on my figure of a dancer here, I won't see that distracting image in the viewport. And that's because we actually cannot turn off the shading of this Sky Dome. The only way we can get rid of that shading is to set the viewport to wireframe. At least in Maya 2020, an Arnold Sky Dome can never be displayed as wireframe in a shaded viewport. The usual methods of template, reference, and drawing overrides don't work. And if we don't want to see the environment backdrop in the viewport, the only option is to push the light object somewhere off screen. Let's go into the Sky Dome attributes. I'll select it and open the attribute editor, Control-A. Scrolling down in the attributes, I just want to point out a few things. In the viewport section, I've set the sky radius to only 20 centimeters. It will not affect the lighting or the backdrop. To avoid rendering that backdrop, up here in the visibility section, I've set the camera visibility to 0. We'll still get the lighting, we just won't get the backdrop in Arnold. Going up a little bit farther, I've set the number of samples to 3, and that's to improve the quality of the rendering and reduce grain without increasing the global sampling settings in the renderer. And finally, I've knocked the exposure down by 3/4 of a stop to negative 0.75, just so that the object will not be overexposed. Okay, that's a typical setup for a high dynamic range environment where we don't want to see the backdrop, either in the viewport or in the rendering. Let's assign the standard surface material to the sculpture. In the perspective viewport, select the sculpture object and frame that selection with the keyboard shortcut, which is F for frame selected. Assign the new material by right-clicking in the viewport. From the marking menu, choose Assign New Material. In the Assign New Material dialog, at the very top we see Standard Surface. The standard surface material has been promoted to the top of the list of favorites in order to promote its use. It really is the way forward for physically based rendering in Maya, in many other Autodesk applications, and really across the whole CGI industry. In the near future, we'll see more and more standardization of material parameters, allowing us to transfer materials between different applications more easily. And the standard surface in Maya is a first step towards that universal compatibility among applications. So click on Standard Surface to assign it. And in the attribute editor, we see that node is selected. Let's rename it. We'll call it Sculpture_STSF for Standard Surface. And press Enter. We also want to rename the associated shading group. Select that string of characters and copy it with Control-C. In the Attribute Editor tabs, select the Standard Surface 3 SG node, which is the shading group, and rename it. Just paste in that string and add an _SG at the end, and press Enter. Okay, I'll go back to the Material Shading node, and let's do a rendering of this perspective view. I'll get in a little bit closer in that perspective view with Alt and right mouse button, and navigate with Alt and middle mouse button. Just track around, get in closer. And with focus on that perspective view, go into the main Maya menus and choose Arnold Render. The Arnold Render view pops up and automatically renders that perspective viewport. Let's just make sure that interactive production rendering is enabled. Click on the Start button, which is currently a triangle in my case, And when we see that it turns to a red square, that actually means that interactive production rendering is running, because this is now a stop button. We can verify that it's running just by manipulating the viewport with Alt and middle mouse, and we see that IPR is running in the Arnold render view. Going over to the standard surface attributes, we see the base attributes, weight, and color. I strongly recommend that the base weight should be at a value of 1, at least as a starting point. The default is 0.8. Let's increase that base weight, or the strength of the base color, to its maximum of 1. And there are a lot of reasons why I recommend this. The most primary is that this color swatch here will only closely represent the final rendering if the base weight is set to 1. So for example, if I click on that color swatch and set it to a bright red, we can see that with the base weight of 1, this red and this fully illuminated red look similar. If I bring that base weight down, then these don't match anymore. And the more I bring that down, the greater the difference is. Okay, so I'll set that base weight back up to a value of 1. And by the way, ignore the material swatch in the attribute editor. The lighting on that sample sphere is very dim, and it does not represent the color of a fully illuminated object in the scene. Moving on to the specular section, those are the shiny highlights. In order to see those more clearly, I'm going to temporarily reduce the base weight down to 0. And we see the default specular weight is 0.2. I recommend bringing that up to its maximum of 1, at least as a starting point, and that's physically accurate. With a specular weight of 1, the shininess of the material is controlled by the roughness attribute here. So if I increase that roughness all the way up to a maximum of 1, I don't get any shiny highlights. The specular weight does come in handy if you want to create certain special effects, or if you want to just simply dim down the highlights, but I do recommend starting out with the specular weight at a value of 1. Okay, we'll finish this up by creating an ideal diffuse material in which all of the incident light upon that object is reflected and scattered. I'll bring the base weight back up to 1 and set the base color to pure white with a saturation of 0 and a value of 1. And now we've got an ideal diffuse material in which all of the light hitting the object is reflected and scattered. Those are the most basic primary attributes of the Autodesk standard surface. Carrying on from the previous movie, I've got the sculpture selected in the viewport. I'm displaying the standard surface attributes, and I've got the Arnold render view running in interactive production render mode. Let's talk about specular roughness. Roughness is a measure of how porous a surface is, and with a value of 1, the surface will be rendered as if it had many tiny micro-fine deviations in its surface, and that will cause the light to scatter around. It's easier to see if we have no diffuse or base color. I'll set the base weight down to its minimum of 0. With a specular roughness of 1, we get this kind of matte finish in which the light is being scattered around in all directions. As we reduce the roughness, we increase the glossiness or shininess of that surface. If we bring it down to around 0.4 or 0.5, we get a kind of semi-gloss surface. If we bring the roughness down to its minimum value of 0, we get a perfectly smooth, glossy surface. It's not at all porous. There are no micro details. It's just perfectly smooth. Currently, we're not really getting a mirror reflection. We're not seeing the full brightness of the reflected environment here. We'll talk about how to achieve that with metalness in another movie. For now, I also want to talk about the diffuse roughness, because that can be a little bit confusing since there are two forms of roughness. This is the specular roughness, which has to do with how porous the surface is. Then we have the diffuse roughness, which affects the base color. And it's more like a larger scale roughness. So you might think of the specular roughness as being really microscopic, but the diffuse roughness being at a little higher scale or a little larger deviations on the surface. So I'll bring the specular weight down to 0, just so we're not confused by that, and bring the base weight back up to 1, and increase the diffuse roughness. And if we bring that all the way up, what we'll see is the light is being scattered even more, and we're getting a look that resembles unfinished ceramic. Okay, that's the difference between the diffuse roughness and the specular roughness. Generally speaking, we can leave the diffuse roughness at its default value of 0, unless we need that special effect. We can accomplish most of what we need using the specular roughness. I'll bring the specular weight back up to 1 and leave the specular roughness at 0 to show that we've got an underlying base or diffuse layer and then a specular layer on top of that. And with a roughness of 0, we're getting the effect of a finished ceramic instead of an unfinished. That's the basics of specular and diffuse roughness. Index of refraction, or IOR, is a measure of the real-world density of a material. And as the name index of refraction indicates, it controls the amount of bending of light as it moves from one transparent material to another. To control the strength of refractions, you adjust the IOR parameter. But notice that IOR is in the specular section, not in the transmission section, which deals with transparency. And the reason IOR is in the specular section is because it also controls the strength of highlights. And it controls not just the strength of highlights overall, but the strength of highlights at different angles to the camera. So to see this more clearly, I'll turn the base weight down to 0. And with a specular weight of 1, we can see those highlights without any other elements present. So with the IOR at its default of 1.5, we're seeing the effect of the density of glass. And there are some presets here for this parameter. There's a tiny little icon here of 3 lines, a so-called hamburger menu. If you click on that, then you get access to a few presets. And if we choose glass, for example, it still says 1.5, but if we choose plastic, then it goes up a little bit. So index of refraction will control the strength of highlights, and if we reduce the IOR, we're reducing the density of the material, and that causes it to become less reflective. If we increase IOR, we're increasing that density and thereby increasing the reflectivity. And with a positive IOR greater than 1, generally speaking, we're just increasing the strength of reflections overall. But with IOR values close to or lower than 1, we start to see a difference between the highlights at the edges and the highlights in the center of the object. So IOR controls the relative strength of highlights if the surface is pointing away from the camera at 90 degrees or towards the camera at 0 degrees along that camera's z-axis. The strength of these highlights relative to one another is based upon something called the bidirectional reflectance distribution function, or BRDF, which is a mouthful, but it's a mathematical function that determines the shininess of highlights, whether the surface is pointing towards the camera or at 90 degrees. As we reduce the IOR down, we'll start to see an even more dramatic bidirectional reflectance distribution function. So with an IOR near 1, we get only the edges and nothing in the camera-facing surfaces. If the IOR is exactly 1, that corresponds to vacuum or air or any perfectly clear gas. Since there's no base weight here, we're not getting anything. We're getting a totally blank rendering. There's an old trick you can play with index of refraction. If you reduce it below 1 into a fractional value, you'll start to see a kind of metallic effect. And that looks good at first blush, but it turns out it's not actually physically accurate. And if you want to get a physically accurate result, you should use the metalness parameter. We'll talk about that in a subsequent movie. Right now, I'm just going to set that IOR back up to maybe a little bit higher than 1.5 for glass. Maybe I'm trying to reproduce the reflectivity of ceramic glazing, which is going to be maybe a little bit more dense than glass. I'll bring that base weight back up to a value of 1. And that's the basics of how to use IOR, or index of refraction, 'to' 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 We saw how index of refraction affects the specularity, or the shiny highlights, of a surface, and how with an IOR below 1 we can achieve metallic effects. Well, there is an easier and better way to get a metal surface, and that's simply to use the metalness parameter in the base attributes. Metalness is a slider that allows us to blend between two different shading modes. With a metalness of 0, we have a completely non-metallic surface here. If we increase the metalness up to its maximum of 1, we get a completely metallic surface. But we can set a value in between and get different effects and different looks. If metalness is 1, you'll notice that the IOR parameter is grayed out. With a metalness of 1, that's equivalent to an index of refraction of 0. The reflections on the surface are at equal intensity regardless of that surface's orientation to the camera. So again, a metalness of 1 is equivalent to an index of refraction of 0. Another important factor with metalness is how it interacts with the specular color. So if I bring the specular color down to 0 or black, I don't see any change here. And that's because metalness will cause the base color to determine the specular color. So although IOR is grayed out, the specular color is not grayed out, despite the fact that it has been disabled. With a metalness of 1, all of the specular color is coming from the base color. If I wanted a gold, I could click on that base color and set that to a gold color here. Increase the saturation, maybe knock the value down a little bit, and you see we've got some very intense gold highlights. To achieve different material effects, we can find a blend between metalness and non-metalness. We'll need to have a non-black specular color to see it. And I've got my specular color up at white. If I reduce the metalness value down to, let's say, 0.75 or so, now we're getting more of a bronze effect instead of gold. Keep bringing that down, and at a value of about 0.4 or so, now we're getting sort of a tinny look. Bring that down even less to around 0.1 or so, and now we're back to a kind of glazed ceramic. And it's actually a little bit better than the glazed ceramic we had before. Adding just a little bit of metalness, let's give that a value of 0.1 and an index of refraction of about 1.6 or so. Now we're getting a much more believable glazing on that material. So that's how to achieve metallic and non-metallic effects with the metalness parameter. Anisotropy is the phenomenon of streaked highlights. The word anisotropy means not all in the same direction. Isotropic highlights are round, anisotropic highlights are stretched in some dimension. And anisotropy is a physical property of a material in which the roughness of a surface has some orientation. We see this with materials such as hair and brushed metal. Let's add some anisotropy to the gold material I've got applied onto the figure of a dancer. I've got the dancer selected, and in the attribute editor, I'm displaying the standard surface material node. I want to be able to see the results in the viewport as I change the attributes. And to do that, I want to deselect the object, so I'm not seeing the selection highlighting. I can just copy the attribute editor tab, and now that's in its own window, and that'll stay up regardless of what's selected. I'll deselect the object in the viewport. And for anisotropy to work, we'll need to have some amount of roughness. With a 0 roughness, we'll see no change. I'll bring the roughness up to a value of about 0.2 or so. Now we've got isotropic highlights. They're all the same in every direction. We have round highlights. As we increase the anisotropy attribute, we'll start to see some directionality emerge. When we bring that up to a value of 0.9 or so, we have some strong streaked highlights. We can change the orientation of those streaks with the rotation attribute. It is designed to normalize 360 degrees of rotation to a 0 to 1 attribute space. That means with a rotation of 0, we have 0 degrees of rotation. But if we increase this a little bit, we'll start to see that it's rotating a bit more than we might expect. If we bring this up to a value of 0.25, we're rotating the anisotropic effect by 90 degrees. With a value of 0.5, we're rotating by 180 degrees. With a value of 0.75, we are rotating by 270 degrees. And with a value of 1, we're rotating by 360 degrees. The rotation attribute is a little bit tricky that way, so if you want to rotate by 90 degrees, you'll set that value to 0.25. With focus on the perspective view, go to the main Maya menu and choose Arnold, Render. When that completes, we can create a snapshot by clicking on the little camera icon in the lower right. And this is the effect we see with anisotropy enabled. Let's change the rotation value. We'll set it back to 0 and let it finish rendering. When that's done, create another snapshot. And we can switch back and forth between these. Here it is with a rotation value of 0.25 and a rotation value of 0. We can see how we reoriented those streaked highlights. And just for completeness, let's go back to our live rendering by clicking on the little eye icon and render it with no anisotropy and see how that compares to the other versions. When that's finished, we can create another snapshot. So here is the version with no anisotropy. Here we have an anisotropy of 0.9 with a rotation of 0. And the first one we made was an anisotropy of 0.9 and a rotation of 0.25. So that's the effect of anisotropy for streaked highlights. Let's look at mapping certain attributes of a shading node which will only accept a floating point input instead of a color. For example, in the standard surface material, you'll see you've got a base color, which is an RGB input, and the base weight, which is a floating point input. It can only accept a single value, not 3 values. I want to map the base weight in this case so that I can have independent control over the base color and the base weight. The effect I want to achieve here is to apply a base color with an RGB value, and also to modulate the weight of that base color so that it will be darker in the recessed areas of the model. I've already got an ambient occlusion map prepared for that purpose. And with the Arnold Render view open in interactive production rendering mode, we can go ahead and make some changes to our shading network in the Hypershade. Click in that Hypershade and let's create a file shading node. Press the Tab key to get the search box and type in FILE and click File Texture. And that creates a file node and a 2D texture placement node. To rearrange the graph, I'll select one of those two nodes and select its entire network with the / keyboard shortcut. I've selected both of those and I can move them over. Now I need to assign the file to the file node. So select that node by itself and open the attribute editor with Control-A and browse for the file. I'm taken to the current project source images. I want to choose Dancer4096 occlusion.png. In the preview, we can see that ambient occlusion map, which is black and white. Click Open. And now we can connect that to the base color. We can take the file node's out color, which is an RGB value, and plug that directly into the base color of the standard surface. Select that material node, and in its attributes, we can see that the color has been completely taken over by that file input. Now, with this setup, I no longer have the ability to add any saturation or change that color in any way, unless I, for example, used a color correction or a remap value node here in between the file node and the material node. Well, that's complicating things unnecessarily, because I really just want to map the base weight. So I'll disconnect the connection I just made. And one way to do that is to use a keyboard shortcut, hold down Shift and Alt, and drag across that connection wire, and that'll delete it. Now we're back to controlling the base color in the usual way. Click on that base color swatch and give it a hue of, let's say, 18 or so, and just a little bit of saturation so that we see we've got some color on there. And now we'll map the base weight. We can't connect the out color directly to the base weight. We could use one of the components of the out color. That's one solution to this. I could click on the plus sign next to the out color label and open that up and just take one of these RG or B values. And since it's a black and white image, it doesn't really matter which one I take, but I'll take the green channel and connect that to the base weight. In the interactive production rendering, we can see we've dimmed down the base color in those recessed areas of the model. So that's one way to do it, but another way, which is possibly cleaner, is to use the alpha channel output. So once again, I'll break this connection with Shift, Alt, and left mouse drag over that wire. Now we're back to no ambient occlusion affecting the base weight. If we connect out alpha directly to base weight, when the interactive production rendering finishes, we don't really see any effect of ambient occlusion. And that's because the output of the alpha channel is null in this case. There really is no transparency in the file. But we can easily make that out alpha channel take the luminance, or the overall brightness. Just select that file node, and in its attribute editor, open up the color balance section, and tick the box labeled alpha is luminance. Just turn that on. And now what's coming out of this out alpha port is the combined brightness of the RGB channels. And now I'm able to further adjust this by playing around with some of these color balance controls, such as exposure or the alpha gain and alpha offset. Set the exposure back to 0. So we've got the alpha offset, which allows us to brighten up the blacks. We've got the alpha gain, which lets us dim down the whites or increase the whites. Set those all back to their default values. That's how to map a floating point input such as the base weight. The coat attributes of the standard surface give us the ability to apply another layer of specular highlights to simulate certain materials such as thick varnish or heavy glazing. I've currently got my figure of a dancer selected. I'm displaying the standard surface attributes. Arnold Render View is running in interactive production render mode. To see the effect of the coat layer most clearly, I want to temporarily disable my base color. Currently, I've got something connected to the base weight, so I can't just dim that weight down with the slider, but I can change the base color to black, and that'll disable the base layer. Click on the base color swatch and set it to black. When the interactive production rendering finishes, let's make a snapshot of that so we can compare it to later versions. Click on Snapshot. And that's the specular component alone, with a roughness of 0.5 and an index of refraction of 1.6 or so. Now let's apply the clear coat. Open up the coat section, and we've got controls very similar to the specular highlight section, starting with the weight. So I'll increase that weight up to its maximum of 1, and we see another layer of highlights here. And they're shiny and more distinct because the default coat roughness is 0.1, and that's a pretty good value for that. I also want to make that coat a little bit more dense, so I'll bring the index of refraction up to 1.7. And to see the difference between these two layers, let's temporarily reduce the specular weight down to 0. And again, when the IPR finishes rendering, make another snapshot. And the first one we made is just the specular layer. The second one we made is the coat layer. We'll go back to a live rendering and increase the specular weight up to its maximum of 1, combining the two layers. That's going to take a lot longer to render, so only use the coat when you really need it for an effect. When it does finish rendering, make another snapshot and we can compare the results. The first snapshot is the specular layer only, the second one is the coat layer only, and the third one is the two layers combined. I can go back to a live rendering and bring back my base color, click on that swatch, and we should have the previous color here in the history. Okay, now I've got all the components in place, and I can adjust their various weights or indices of refraction to get the result that I want. That's how to apply a clear coat effect using the standard surface coat attributes. Subsurface scattering is the phenomenon of light bouncing around and exiting a translucent material. I've got my figure of a dancer selected. I'm viewing its standard surface attributes in the attribute editor, and Arnold Render View is running in interactive production mode. I'm going to make a snapshot of this version of the material with no subsurface scattering and a base weight of 1. To make the subsurface scattering effect more clear, I'm going to temporarily reduce the specular weight down to 0. And when that finishes rendering, I'll make another snapshot. What we see here is just the base layer with no specular and no subsurface. I'll close the specular section just to make some space, and then open up the subsurface section. Increase the weight up to its maximum of 1, and we start to see a ghostly figure here. The object has turned white because the subsurface color has completely taken over the base color. Increasing the subsurface weight subtracts from the base weight, although that is not really indicated in the interface. What's going on here is the base component is the incident light that's scattered by the surface. It's also known as the diffuse reflection. But for some types of materials, such as wax or skin, some of the incident light actually penetrates the surface and scatters within the volume. Some of the light inside the volume is absorbed, but some is not absorbed and is reflected back outside the volume and is visible to the camera or an eye. The total amount of scattered light inside and outside the volume cannot exceed 1.0. So as we increase the subsurface weight, we're always reducing the base weight. If the base weight is 1, and for example, we set the subsurface weight to 0.5, then the effective base weight is actually 0.5. Our actual base weight range here is now between 0 and 0.5. Okay, I'm going to set the subsurface weight up to its maximum of 1, which actually is physically accurate. Then we come to the color swatches here. We have the subsurface color. You can think of that as the deep or thick regions of the volume. If I click on that color swatch and set it to a fully saturated red, we can see how some of the areas on the model are white, and that's the radius color, and some of the areas are red. That is the subsurface color. Now, it may seem a bit strange that the radius is an RGB color rather than a single scalar floating point value. Usually a radius is just a single value, not 3. But here we can set a different radius for each of the red, green, and blue channels in order to tint the color. For example, if the radius color was set to red, then red light could travel farther and be absorbed less. And the end result would be red tinting in these shallow regions. But you need to beware of supersaturated colors, such as a solid red, because those can lead to rendering errors. Usually you'll just leave the radius at white, or else use the same color that you're using for the subsurface. Let's do that. I'm going to set the subsurface color to match this base color. Click on the subsurface color swatch. I'll set the hue to 18, the saturation to 0.35, and leave the value at 1. Press enter. And that's the result we get with radius set to white. And in these thin areas, we're getting a white color. Let's also set the radius to that same color. Click on the radius swatch, and we can just use the color history to plug in that same color. And now we get a lot more saturation. The subsurface scale parameter is a multiplier for the radius. Usually you'll set the radius to the color you want, and then adjust the scatter distance with the scale. If we have a lower scale, then we'll reduce the amount of light intensity, reduce the distance the light travels, and increase the absorption. I'll set the scale to a value of 0.1. And now that's a more realistic effect, where the light's not penetrating quite so deep into the model. Then we come to anisotropy. Subsurface anisotropy is not like specular anisotropy. It's not the shape of the effect, but the directionality relative to the incident light. A value of 0 scatters the light evenly in all directions. A negative anisotropy gives backscattering. The subsurface light is reflected back towards the light source, and it's almost the same as a pure diffuse reflection. If the anisotropy is positive, we get forward scattering. The light continues to travel in the original direction of the light rays and actually passes through the object. Usually we want the anisotropy to be a value of 0 to scatter light evenly in all directions. We can art direct this by reducing the subsurface weight and bringing back some of the base component. I'll set the subsurface weight to 0.5 for a 50% blend between the subsurface and base color. Combining the subsurface and base components is going to make the render time a bit longer. When that's finished rendering, make another snapshot, and we can compare these versions. Here's a version with no subsurface scattering. Here's a version with 50-50 blend between subsurface and base component. Finally, let's re-enable our specular component, bring that back up to a weight of 1, and let that finish rendering as well. When it's finished, once again make a snapshot, and we can compare that to the version with no subsurface scattering. In the final version, we have the base, specular, and subsurface components enabled. And in this version, we have just the base and specular. So we can switch back and forth between these to see a pretty good real-world example of how to apply subsurface scattering. The standard surface not only reflects light in the scene, but also allows the surface to emit light into the scene. In this version of my museum scene, the figure of a dancer has a material assigned to it with all of its shading components disabled, and I have no lights currently active in the scene. If we do a rendering with Arnold Render, we'll see that we get a completely black screen. I'll select my dancer figure and open the attribute editor with Control-A. And in its standard surface attributes, we can see that I've disabled the base weight, specular weight, and everything else. Let's go into the emission section and increase the emission weight up to 1. And now we see that surface is emitting light into the scene. It's going to be pretty grainy, especially because the shape of this dancer figure is quite complex. If you had a simpler shape such as a sphere or a torus, the end result of the emission would be less grainy. Once that finishes rendering, I'll make a snapshot. Go back to the emission weight, and we can increase this beyond 1. One of my favorite features of Maya is the soft limits in the attributes. We can push the weight beyond 1, even though this slider maxes out at 1. Let's set the weight to a value of 5. And as that renders, we can see that it's quite a lot brighter. When that finishes rendering, once again, I'll make another snapshot. If we get in really close on the silhouette, we'll start to see some issues with the rendering. I'll zoom in with Alt and right mouse button and track around with Alt and middle mouse button. If we switch between these two snapshots, we'll see that the first one has got nice anti-aliased edges on the silhouette of the figure. The second one, with an emission weight of 5, shows some very crunchy and aliased edges, and we're also losing some definition in that silhouette. The hands and fingers are not resolving as well as they do in the other rendering. This is happening because the light is so bright that it's overwhelming the renderer's anti-aliasing. We can correct for that by clamping the anti-aliasing. So I'll click to go back to a live rendering, open up the render settings, go into the Arnold Renderer tab, open up the clamping section, enable clamp AA samples, and set the AA clamp value to 1. And now as that renders, we will start to see that we're getting a nice soft edge on the silhouette of the dancer. When that's finished, we can go back to a 1-to-1 view and store another snapshot. So here's the first version with the weight of 1. Here's a weight of 5 and no clamping. And here is a weight of 5 with clamping enabled. And we can see there's quite a visible difference there in the edge. Click on that again to go back to a live rendering. We'll also need to increase the number of diffuse samples to avoid this very grainy illumination. So in the Arnold Renderer settings, we can increase the number of diffuse samples up to 10. That's going to take quite a lot longer to render, but it will eliminate a lot of the grain. When that's finished, once again, I'll store a snapshot. The material emission method can be a bit grainy. If you want to explore a different workflow, you can try using an Arnold mesh light and increase the samples on that mesh light. And that could give you a better result if you're just using a flat color for the emission. If you want to use a texture, then you probably do want to use the material emission method because that's going to be a bit more accurate. So for example, I can go back to the attribute editor and in the emission color, click to create a new render node. And I'll go to 3D Textures and choose Crater. Go to the Place 3D Texture node and just increase the scale in X, Y, and Z up to 10. Type in a 10, press Tab, 10, press Tab, 10, and press Enter. And now I've got a nice texture on there. And as that renders, we can see that we're going to get a pretty accurate result, especially down here at the bottom where the surfaces are contacting. A primary advantage of using the material emission color instead of an Arnold mesh light is that if you've textured that material emission color, it's going to be more accurate than a textured mesh light. That's how to use the standard surface to emit light into the scene. Transparency is handled by the transmission attributes of the standard surface. In this version of the scene, I'm using an Arnold sky dome to provide illumination and a backdrop. I've also enabled a depth of field effect in the camera in order to differentiate the foreground and background. We don't have time to cover those techniques in this course, but if you're interested, you can check out my other course, Maya Rendering with Arnold 6. I've got the sculpture selected. I'm displaying the standard surface attributes in the attribute editor. The Arnold render view is open and interactive production rendering is enabled. Once that's finished, I'll create a snapshot so we can compare it to later versions. In the attribute editor, I'll open up the transmission section and increase the transmission weight from its default of 0 up to its maximum of 1 for a perfectly transparent surface. When that's finished, I'll create another snapshot. The default index of refraction is 1.5, and as we discussed earlier, index of refraction determines the density of a material. A higher IOR will cause light rays to bend more as they enter or exit a solid transparent object. An index of refraction of 1.5 corresponds to ordinary glass. But if this were a crystal sculpture, it would probably be more dense than ordinary glass. I'll increase the IOR up to a value of 1.7. When that's finished once again, I'll create another snapshot, and I can stop the interactive production rendering and compare these two versions. This snapshot has an IOR of 1.7, and this one has an IOR of 1.5. And we can see the difference as we switch back and forth between those two. Currently, I've got a transmission weight of 1. Notice that the base weight is grayed out. If transmission weight is equal to 1, then the base color is disabled. You'll get no diffuse reflections. But transmission weight does not affect the specular component. Also, if the transmission weight is set to any value other than 0, then Arnold will automatically disable the opaque attribute of the object's shape node. If I go into the Dancer Shape tab in the Attribute Editor and open up the Arnold section, we'll see a flag labeled Opaque. The opaque attribute optimizes ray tracing by determining if transmission rays are calculated for that shape. If opaque is on, then no transmission rays are calculated. Well, we can clearly see that we've got transmission rays here. With a non-zero transmission weight, Arnold automatically disables the opaque attribute, allowing the transmission rays to be calculated. Transmission weight only affects the opaque attribute if opaque is enabled. If you disable opaque, then transmission rays will be calculated even if the transmission weight is 0. In that case, you'd be calculating transparency for an object that is actually opaque. That's not a good idea. It would lengthen render times unnecessarily. The smart move is to always leave opaque enabled. And anyway, this attribute may be removed in a future version of Arnold. Since no solid material is perfectly transparent, we probably don't want to have a transmission weight of 1. I'll go back to the standard surface and set the transmission weight down just a little bit to 0.98 or so and re-enable interactive production rendering. That's going to give us a little bit of diffuse reflection, and since the base color is white, it's going to brighten the surface a bit. When that's finished, once again, I'll create another snapshot. Here's a version with a transmission weight of 1, and here's a version with a transmission weight of 0.98. We brighten the surface a bit by reducing the transmission weight to 0.98 and allowing a little bit of that base color to show through. That's the basics of the transmission attributes for rendering a transparent refractive volume. For colored transparent surfaces, such as tinted glass, use the transmission color and depth attributes of the standard surface. In this version of the scene, I've got the transmission weight up to its maximum of 1 and the color set to white. And I've got a rendering here. I'll store that as a snapshot. In the standard surface attributes, let's change the transmission color. Click on that color swatch and set it to a fully saturated blue. And Arnold Render View is running in interactive production rendering mode. We can see that we've got a very highly saturated blue color. This is a very simple effect in which the color reaches its full intensity at the surface of the object. The color is applied at the polygon surface, and the shader has no interaction with the volume contained by the polygon mesh. When that's finished rendering, I'll create another snapshot. For a more realistic effect, the depth parameter allows us to set a distance within the volume where the transmission color is reached or achieved. That simulates the effect of light absorption. As light passes through a colored transmissive material, some of the light will be absorbed. The more volume the light passes through, the more light is absorbed. The absorption near the boundaries of that volume will be less than in the center. Visually, the material will look darker in the center of the volume. To see this effect, we'll need to reduce the saturation of the transmission color. If it's fully saturated, there won't be any way for the color to build up inside the volume, since it's already at its maximum. I'll click on that color swatch again and set the saturation to 0.5. When that finishes rendering, once again, I'll create a snapshot. And let's increase the depth parameter. Bring that up to a value of 2 centimeters. And we see the color change. The transmission color that we chose is not the color that we see on the screen. That is the color at the depth distance. With a low depth value such as 2, we get a lot of accumulation of that color inside the volume, and it's pretty saturated. I'll create another snapshot. With higher depth values, the color won't accumulate as much. Let's increase the depth up to a value of 10. And now it's quite a lot less saturated. When that's done, I'll make another snapshot. And just for illustration purposes, if we increase the depth amount too much, up to a value of, let's say, 100, then the transmission color doesn't have a chance to accumulate within the volume at all. The depth distance of 1 meter or 100 centimeters is now completely outside of the object, and the transmission color has very little or no effect. The optimal look I wanted here was a depth of 2, and we've got that stored in a snapshot already, so let's turn off the interactive production rendering and look at our snapshots. Here's a render with a highly saturated transmission color and a depth of 0. Here is a desaturated transmission color and a depth of 0, and a depth of 2, and a depth of 10 centimeters. So here's the sweet spot I wanted with a depth of 2, and we can see in the thicker parts of the model, we've got more saturation, and in the thinner areas, such as the hand and this gown, we're getting less saturation. That's how to work with transmission color and depth for tinted glass and other colored transparent materials. Picking up from our discussion of transmission and specularity, I want to talk a little bit about how to achieve certain effects such as frosted glass or very dense, thick liquids. Currently, I've got a version of my dancer with a tinted transmission color and a specular roughness very low, a value of 0.05. And that would correspond to a polished glass. I'll make a snapshot of that. For a frosted glass effect, I would increase the specular roughness. Bring that up to, let's say, 0.4 or so. And let that finish rendering. When that's done, store another snapshot. And we can compare these. Here's a roughness of 0.05 and a roughness of 0.4. The roughness is at the surface of the material. In other words, we've simulated the effect of the outer surface of the glass being frosted. But if we wanted the effect of the interior of the material scattering light, then we would use transmission scatter. So I'll go back to a live rendering by clicking on that snapshot again. I'll set the roughness back down to 0.05, and I can increase the transmission scatter amount. And let's bring that up to a pretty high value, about 3/4 of the way up. And we'll start to see the effect of light scattering around inside the material. We still have very well-defined shiny highlights because the roughness is 0.05, but having increased the transmission scatter amount, now light is bouncing around inside the material. Transmission scatter works very similarly to subsurface scattering for the diffuse or base color. In this case, we have no diffuse component or no base color, and the scattering is all dealt with by the transmission attributes. And when that finishes, store another snapshot. Let's compare that to the first rendering here. So that is a scatter amount of 0, or a color of black. And here we have a scatter value of about 0.7 or 0.8. Notice that we've reduced the saturation. That's because the scatter color is monochrome. If we wanted to simulate different frequencies of light scattering by different amounts, we could give the scatter color some tint. I'll click on that color swatch and set it to a saturated blue, but then reduce the saturation down to 0.5. And now I've got the same color for the transmission color and the scatter color. I'll click on that snapshot and go back to a live interactive production rendering. Once again, when that's finished, I'll create another snapshot and compare. Here's a version with a light gray scatter color and a version with a blue scatter color. I'll click on that snapshot again to go back to a live rendering and complete this demo by bringing the specular roughness back up. I'll set that to a value of 0.4. And now I'm combining the frosted glass effect with specular roughness with the internal scattering from transmission scatter. And once again, when that's completed, make a snapshot, and we can compare these. Here's a version with no roughness and no scattering, roughness only, scattering only with a white scatter color, scattering only with a blue scatter color, and finally roughness and scatter both combined. That's how to work with specular roughness and transmission scattering for a frosted glass effect. Usually we'll assign a material to an entire object, but there are some situations in which we'll want to assign a material to a face component selection. Here's an example. I've got a glass case around the sculpture. Give focus to the perspective view, and from the main menus, choose Arnold, Render. We can see that the edges of the glass are darker, but they're not tinted. If this were a real-world piece of glass, then we would probably see some green tinting at the edges due to optical phenomena having to do with impurities in the glass and the way light bounces around inside the glass. When light reaches the edge, it will be partially absorbed and also tinted by those impurities. Although the standard surface and the Arnold renderer are both physically accurate, there will always be limits to what they can accurately simulate, and will need to cheat. And this is a case in which we could assign a different material to the edge of the glass to achieve that optical effect. I'll make a snapshot of this rendering and close the Arnold render view. I've got the Hypershade open, displaying the glass STSF material shading node. I'll select that and make a duplicate with Control D. Select that duplicate and open up the attribute editor with Control A, and I'll rename it Glass Edge STSF and press Enter. In the transmission section, I've got a weight of 0.999 and a color which is very, very slightly green. Click on that color swatch and we'll see you've got a saturation of 0.01. Let's bring that up a bit to, let's say, 0.4. And now we've got a much more green tint to that transmission color. And we want to assign this glass edge STSF to just the edges of the glass. I'll close the attribute editor, minimize the Hypershade, go over to this front view and select the top pane of glass. And zoom in on that with the F key. We'll go into Face Component Selection mode, right-click in the view and choose Face. And we want to select just the faces along that edge, not the top or bottom. So drag a very skinny selection rectangle to only select the edges. And we can check that in the perspective or camera view. It looks like we've selected what we want. And with that selection made, go back to the Hypershade, right-click near the top of Glass Edge STSF, and from the marking menu, choose Assign Material to Viewport Selection. It looks like Hypershade decided to reorganize my graph for me, but we can see this a little bit better if we reorganize it manually. So now we've got Glass STSF and Glass Edge STSF, and we've got a new shading group node for Glass Edge STSF. Let's render that and see what it looks like. Give focus to the perspective view. Once again, go to Arnold Render. And when that finishes, we can see we've got a green tinting on that top pane of glass. All right, let's do the same for the other 4 panes of glass. I'll close the render view, minimize the Hypershade, and go back to Object Selection. Right-click in that front viewport, and go back to Object Mode. We want to select just one of these other panes of glass. We only need to do this once because those other 4 panes are instances. Select one of them and frame it with the F keyboard shortcut. For better accuracy, I'll probably want to maximize that front viewport. So tap the space bar. And once again, go into Face Component mode. There's another way to do that, which is the F11 keyboard shortcut. Once again, draw a selection rectangle to only select the faces on the edge and not the front and back. Tap the spacebar to go back out to a 4 viewport layout. We can see that we've selected components on all of the other instances. Go back to the Hypershade. Once again, right-click near the top of Glass Edge STSF and choose Assign Material to Viewport Selection. I'll mention that we could drag and drop into the viewport, but I prefer to do it this way because it's a lot more precise. All right, we can go back to Object Mode, right-click and choose Object Mode. Give focus to the perspective view. And once again, Arnold Render. Once that's done, we can make another snapshot and disable interactive production rendering. Let's compare these snapshots. Here's the one with the same transmission color for all faces. And here's the one where we've increased the transmission color saturation for those edge faces. That's how to assign materials to polygon components. For single-sided geometry that has no volume, you'll want to enable the thin walled option in the standard surface to avoid unnecessary calculations. In this case, I've got a plane of glass over the front of this picture, and I want to enable the thin walled option to avoid calculating refractions or transmission depth or any other expensive ray tracing, and I'll only get just a simple transparency and reflections. I want to select that pane of glass, and it's a bit difficult because it's just a single polygon. I'll do that from the outliner. Open that up, and also open up Picture Lighthouse Locator. Within there, select Glass Lighthouse. And now that's selected, open up the Attribute Editor with Control A and go to the Glass Picture STSF shading node. And we'll see that we've got transmission weight of 1, and you can see that the depth, scatter, and other fancy transmission attributes are all available. But because this is a flat plane and single-sided, none of this really applies. There is no depth because there is no volume. So scroll down, and in the Geometry section, enable Thin Walled. And as soon as we do that, we see all of those fancy transmission attributes are grayed out, and we only have a color for the transmission. We can do a rendering of that. Go to Arnold Render. And when that finishes, we can see that we're getting nice reflections and transparency, but we're not calculating any refraction or fancy depth or scatter effects. That's how to enable thin-walled geometry to optimize ray tracing for single-sided surfaces. A cutout map, or a geometry mask, will prevent any component of the standard surface material from rendering in a certain location on an object. We'll use it in this case to mask off the black parts of this leaf texture. I've got the Hypershade open displaying the material shading network for Houseplant 05 leaf standard surface, and I've got the Arnold Render view running with interactive production rendering enabled. As we saw in the previous movie, we can optimize ray tracing by enabling thin-walled geometry because these leaves are single-sided surfaces. Select the standard surface material in the Hypershade and open up the attribute editor with Control A. Scroll down and open up the geometry section and enable thin walled geometry. We can close the attribute editor. And now let's map something to this opacity channel of the standard surface. I've already got a base color and a bump map. I'll make a duplicate of this base color file node. The reason I want to make a duplicate is to maintain the connections to this place 2D texture node. If I ever want to change the mapping, I can do it from a single node. Select the base color file node, which is labeled Houseplant 05 Leaf. Go into the Hypershade menus and choose Edit, Duplicate with Connections to Network. Now we have a new file node, but it's been placed over here kind of inconveniently. We'll navigate with Alt and middle mouse and grab that file node and move it into position. With that file node selected, open up the attribute editor once again with Control A, and let's rename it Houseplant 05 Leaf Opacity. Then navigate for the image, click on the Browse button. In the Project Source Images folder, we want to choose House 05 Leaf Alpha.tga and click Open. We can close the attribute editor now, and we'll make the connection. Once again, track in the Hypershade view with Alt and middle mouse button, and connect that out color port to the opacity of the standard surface. And immediately in the Arnold render view, we see we've got a cutout map. That's how to apply an opacity map to mask off all components of the standard surface. We've seen how to simulate small scale and microscopic roughness. Now let's look at surface relief, which is roughness on a larger scale. The easiest way to simulate surface relief is with a bump map. I'll use that to apply a rough texture onto this plinth or pedestal. I've got Arnold Render View open and interactive production rendering enabled. In the Hypershade, I'm looking at the plinth standard surface material. I've got a texture already prepared for this. Let's go to the Textures tab of the Hypershade browser. And I've got a node in here, Walls Bump Volume Noise. Middle mouse drag that over into the graph. And we can't connect it directly to the material. We need a bump node. So let's create that bump node. I'll just track over with Alt and middle mouse. Click in the graph and press the Tab key to get the search box. And type in Bump 3. The volume noise texture is a 3D procedural texture, so we'll need a 3D bump node. Click on Bump 3D, and then connect its out normal output to the normal camera input on the plinth standard surface. The Arnold render view updates, but since we have nothing connected to this bump node, we don't see any visible change on the screen. The bump value input is a single floating point input. We cannot take the out color, we have to take the out alpha. So connect out alpha to the bump value, and now we see a very strong bump effect. We can adjust the amount of bump by selecting that Bump 3D node and going into its attributes with Control A. And we have the bump depth amount. We can just bring that down until we see the result that we want. Let's set it to a value of 0.2. Now that's a little bit more reasonable of an effect, but it's still a bit too strong for what I want to achieve here. So I'll bring that bump depth down to a value of 0.1. The scale and other parameters of this bump map will be controlled by the texture itself. So if we wanted to adjust the look, we could go into the volume noise attributes and change those up. Or maybe select the Place 3D texture node and scale up the volume noise. Currently, I'm not seeing the Place 3D texture node in my graph, but if I select the Material Shading node and graph the input and output connections, we'll see the entire graph. And I can zoom in with Alt and right mouse button. Here's the Place 3D texture node. I could go into its attributes and change the scale, entering 10 and pressing Tab to go to the next field. And now I've just increased the scale of that bump map. That's how to apply a 3D bump map to the standard surface. Normal mapping is a variation on bump mapping that gives better results, especially for real-time games, simulations, and virtual worlds. A bump map uses the brightness of an image to simulate height above a surface. A normal map uses red, green, and blue channels to simulate surface deviations in 3 dimensions, giving better fidelity. I've got the shading network for the Dancer standard surface displayed in the Hypershade, and I've already got a file node connected to the base weight. I'll make a duplicate of that file node to preserve the connections to the Displace 2D texture node. Select the file node, and in the Hypershade menus, choose Edit, Duplicate, with Connections to Network. And now we get another file node we can navigate with Alt and middle mouse. Grab that file node, and also go into its attributes. Select it and open the attribute editor with Control A. First, let's change the name of the node. We'll call it Dancer Normal Bitmap, and press Enter. Then browse for the image. Click on the folder. In the current project source images, choose Dancer 4096 normals.jpg and click Open. Very importantly, we need to disable color management for this node, otherwise the normals will get mangled. Set the color space to raw. Back in our shading network, we also need a Bump 2D node. Let's create that. Click in the graph and press the Tab key to get the search box. Type in BUMP2 and click Bump 2D. We need to connect the file node output to the Bump 2D input. As I said before, a normal map relies upon the RGB channels. So you might think that we would connect the out color to the bump value, but we can't do that because the bump value will only accept a floating point input. In the special case of a bump node, we can take the out alpha of a file node and connect it to the bump value. And in this case, we're not actually taking the transparency of this file. We're taking the combined vector of its RGB channels. We also need to change a setting in the Bump 2D node, so click on that and go to its attributes. The Use As pull down is defaulted to Bump. We need to change that to Tangent Space Normals. And that's a format for normal maps in which calculations are relative to the object's surface. All we need to do now is connect the out normal of the bump node to the normal camera on our material node, and we'll start to see a normal map effect. Go back to the attributes in that Bump 2D node and increase the bump depth. You can see that a bit more clearly. So we got a bump depth of about 5 here. That's too strong. Let's bring that back down to a value of 2. Normal mapping is a very powerful and essential tool for game developers and anyone working in real-time rendering engines, because we can dramatically reduce polygon counts by 95% or more while maintaining the same approximate visual fidelity. That's done by sampling the surface normals of a high level of detail model and projecting those normals as a map onto a much lower level of detail model. I've got a rock here that's a high LOD object, and I'm going to duplicate it and reduce that level of detail. And in the following movie, I'll project the normals from one object to the other. First, let's check in on the polygon count. In the main Maya menus, go to Display, Heads-Up Display, Poly Count. The leftmost column displays the totals for the entire scene. The middle column displays totals for the selection. And if I select that rock object, we'll see it has over 30,000 triangles. Now let's make a duplicate. With that object selected, go into the main menus and choose Edit, Duplicate. And in the outliner, rename that new object. We'll call it Rock Low LOD. We'll now reduce its polygon count. In the modeling menu set, choose Mesh, Reduce. And if you get the pop-up in View Editor, you can just reduce the percentage right there. We can set the percentage value to 98%. And now the polygon count for the selected low LOD rock is only 572 triangles. If you're not getting that in View Editor, you can also use the Attribute Editor. Control A to launch that Attribute Editor. And here we could also reduce that polygon count by 98%. That's created a construction history node. We probably want to erase that. If we select Rock Low LOD once again, we'll see that there are a whole bunch of nodes in here, including that Poly Reduce 1 node. Let's just annihilate that history and simplify our scene. Go into the main menus and choose Edit, Delete by Type, History. And now we've just got a raw mesh shape. Now we've got two rocks superimposed over one another. we could grab the Move tool and just move one of them off to the side. The low LOD object has only 572 triangles. The high LOD object has over 30,000 triangles. Okay, we want to move that back to where it was so that those two objects are perfectly superimposed for the purposes of projecting normals. So I'll select that low LOD object, go into the channel box, and just reset its translate Z value to 0. Now we've got a high LOD and a low LOD object, and we're ready to transfer normal maps in the following movie. In the last movie, we created a low level of detail object to receive the projected normals of a high LOD object. Now we're ready to transfer those maps. Select Rock Low LOD in the outliner. Go into the Rendering menu set. And from the Lighting Shading menu, choose Transfer Maps. Now because we selected the low LOD object first, its shape node has been plugged into the Target Meshes section automatically. Open up the Source Meshes section, and here will be listed all of the objects which are going to project onto the target meshes. By default, it says All Other Meshes. And that would actually work in this case because the only other mesh in the scene is Rock High LOD. But we can also explicitly choose that. In the outliner, select Rock High LOD, and in the Transfer Maps dialog, click Add Selected. And now it's listed here. Scrolling down, in the Output Maps section, we can choose which attributes we want to project. Click on Normal. And now a Normal Map section has been added, and we want to choose a file output location, file name, and file type. Click on the Browse button. Go to the current project's source images, and give it a file name of Rock Normals. From the Files of Type pull-down, choose PNG as the file output type. And click Save. That doesn't actually save anything, it just stores the file name, path, and format. We do want to check in on the map space and make sure it's set to the default of tangent space. Tangent space normals are calculated relative to the surface. Scrolling down to the Connect Output Maps section, by default it's going to create a new shader and connect these new maps to that new shader. So we'll leave that alone. Go into the Maya Common Output section, and we want to increase the resolution. Obeying the rule for real-time simulations and game engines, the file resolution should be powers of 2. Set the map width to 2048 and press Enter. And because Keep Aspect Ratio was enabled, the map height updated as well. With all those options enabled, we can go ahead and click Bake and Close. And that'll take a few seconds to calculate. Once that's finished, we can check our work. Select Rock Low LOD in the outliner and grab the Move tool. Just move that rock over to the side. And in the heads-up display we enabled in the previous movie, we can see that it's only got 572 triangles. But if we deselect it, we see a lot of detail on that surface. We can track in the view with Alt and middle mouse, tumble with Alt and left mouse. If we look at the silhouette, we can see that it's still a bit blocky because of the low polygon count. We're not getting good curvature around the edges as we do on our original object. Also, the shading is different because the original object had a standard surface material, and our new low LOD object has a Lambert shader applied. So let's open up the Hypershade and rearrange the graph. Here's the standard surface assigned to the high level of detail object. Right-click in the graph and just make sure that additive graphing mode is enabled. And then select the low LOD object. In the Hypershade menu, choose Graph, Graph Materials on Selected Objects, and rearrange the graph once again. Here's the material shading node applied onto that object, and it's a Lambert. Let's make a duplicate of this standard surface, which is the high LOD material. Select Rock High LOD standard surface and duplicate it with Ctrl D. Select that node and get in closer with Alt and right mouse button. And we can rename it directly here. So just click on the name and we'll rename it to Rock Low LOD STSF and press Enter. And then assign that onto the rock. So select the low LOD rock. Right-click near the top of that node and choose Assign Material to Viewport Selection. Once that's done, we can connect our bump 2D node. Just connect the out normal of the bump 2D to the normal camera of the ROC low LOD STSF. Now we've got the result that we wanted, which is we've got a standard surface material with identical parameters applied onto both objects. The only difference between these two materials is that this one has got a normal map and this one does not. That's how to project normals onto a low level of detail object using transfer maps. Bump and normal mapping only give the illusion of surface relief. It's a trick of the renderer. To actually deform a surface using a texture, use a displacement map. I've got the Hypershade open displaying the graph of the dancer standard surface. Arnold Render View is also open and running in interactive production rendering mode. I'll make a snapshot of the undisplaced surface. Displacement in Maya is handled through the shading group. The shading group is, of course, a node at the end of the material tree, and it's what connects materials to objects and lights. We can see that our dancer standard surface material out color is connected to the surface shader input of this shading group node. To displace an object, connect something to the displacement shader input of the shading group, and that's a special node called displacement shader. Let's search for it. Click in the Hypershade graph, press the Tab key, and type in DISP, and click displacement shader. It comes with its own shading group. We don't need that. We want to connect the displacement shader output to the displacement shader input of the shading group of our object. Then we can select that new shading group node that got created and delete it. Now we'll connect something to the displacement input. Let's create a volume noise texture. Once again, click in the graph, press the Tab key, and type in VOLUM, and click Volume Noise. It's created with a texture placement node. Let's select them both with the slash key on the keyboard. Move that over and navigate in the graph with Alt and middle mouse. Take the out alpha of the volume noise and connect it to the displacement input of the displacement shader. And we see something quite strange over here in our Arnold Render View. We need to change up some attributes. Select that volume noise node and open its attributes with Control A. And scroll down. In the color balance section, enable alpha is luminance. And now we see a highly detailed surface. But there's too much displacement, so it's kind of creating a chaotic situation. Go into the displacement shader attributes and set the scale to a value of 0.2. With an appropriate level of displacement, we can art direct the displacement texture. Go back to the volume noise, and in its primary volume noise attribute, set the noise type to Perlin and set the frequency to 2. And now we've got a more reasonable result in the Arnold Render View, so we can go back over there and create another snapshot. Here's an undisplaced model and a displaced model. Click on that snapshot again to go back to a live rendering. Every renderer will deal with displacement differently. Currently, of course, we're using Arnold. We don't have time to go into all of the options for displacement mapping in Arnold, but I covered that in another course, which is Maya Rendering with Arnold 6. And it talks about subdivision displacement, among other things. In this course, I just want to discuss one of the Arnold options, which is Auto Bump. As the name indicates, Auto Bump applies an automatic bump map to a displaced surface. It does that in order to resolve surface details that are smaller than a polygon. So we could subdivide the surface and create more polygons, or we could apply an auto bump. And auto bump is the default behavior. Let's see the effect of disabling auto bump. Select the object in the scene, and in the attribute editor, in its mesh shape node, open up the Arnold section. You want to scroll down into displacement attributes and open up auto bump. Now there's actually a bug in this version of Arnold, and that is, even though enable auto bump is globally disabled by default, camera primary is enabled by default. And this is kind of very strange. If any one of these is enabled, it's actually going to override the global setting. In your version of Arnold, that might not be the case. But here, in order to disable auto bump, I actually have to turn it on, turn camera primary off. And now we see the effect with no auto bump. It's only displaced the geometry. So we see the triangular structure of that scanned geometry. Okay, we do want to have the auto bump enabled, so I'll turn camera primary back on again. That's the basics of displacement mapping in Maya. In this course, we focused on physically based rendering with the standard surface. Since Maya is seemingly bottomless, there's always more to learn. We've got other courses in the library to help you extend your knowledge. If you're an Arnold user, I invite you to take a look at my courses on lighting and shading with the Arnold renderer. The most recent is Maya Rendering with Arnold 6. I hope you got what you needed from this course, and thanks for watching. Goodbye.